How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at the solution process. So our objectives will be to describe what occurs during the process of dissolving at a molecular level and explain the underlying properties that determine if two things will be soluble and the enthalpy changes with such a process. So we're going to start with a new vocab term, entropy. So entropy has to do with how messy things are. So nature favors things getting messy and all mixed up. If you think about having, like, if you had two separated gases and you got rid of that wall between them, they're going to mix together all on their own, right? You get rid of that wall, come back later, they're all mixed up. You didn't have to do anything. They've gotten messier all on their own. So entropy is the measure of disorder in a system. Nature favors things with higher entropy. So if you take a look, the image on the right has higher entropy because it's all mixed up, whereas on the left, it's lower entropy, it's more organized. So when we're forming solutions, we're mixing things up, so nature favors them mixing. All right, so example, probably real easy. Most people probably be somewhat familiar with this. If you took salt and you mixed it with water, you know you're dissolving that salt, right? I stir it up to speed up how quickly it's dissolving. And then, I got a solution. I got some salt water. So what's happening at the molecular level? Well, the ions in the salt are going to be attracted to the oppositely charged regions on water. So if I'm looking at this water molecule, the oxygen end is going to be slightly negative. The hydrogens are going to be slightly positive. So the oxygen end is going to be attracted to the sodium ion in the salt. And then the chloride ion is the opposite way. Hey, since the chloride ion is negatively charged, it's going to be attracted to the positively charged hydrogens. Now the water molecules are going to come in, they're attracted to those ions, and they're going to break apart those ions from the solid, and that's what's happening when it dissolves, right? So vocab, solute is the substance that gets dissolved. So in this case, it's the salt. Solute would be the salt, because it's getting dissolved. The solvent is the thing doing the dissolving. In this example, it would be the water. And the solution is when the two are mixed together. The solution is the mixture. So one more new vocab is solvation. So solvation is the solvent molecules interacting with the solute particles. So what's happening right here, that is solvation, right? When it's water as the solvent, that solvation we call hydration, because water being hydrated, you're using water to dissolve it, hydration. So let's take a look at the energies involved in all of the interactions that are going on. In order for things to dissolve, what must happen? Well, first, we need to break the attraction between the solvent molecules because we need them to interact with the solute. So that whole process is going to be endothermic. Those solvent particles are attracted to each other. We got to separate them. That's going to take some energy. Now, the same thing has to happen with the solute particles. They're in this nice crystal structure. We have to break them apart. So that's also going to be an endothermic process. But now we can make interactions and attractions between the solute and the solvent particles, which will be exothermic. Those things are coming together. They're going to release some energy when they mix. Now, overall, dissolution can be exothermic or endothermic. So the first two steps are endothermic. The third step is exothermic, but that last step, you can release more energy or less energy than you had to put in. So here I have an example. I have a thermal camera image. On the left, we have an exothermic overall process, and on the right, we have an endothermic process overall. You can see it's getting really hot at the bottom where all that salt is, and when I stir it up, that heat will start to dissipate because I'm mixing the whole thing, and then the opposite's happening on the right. It's getting colder and colder, and if we jump ahead a little bit, you can see that, hey, they're both dissolving things, but on the left, overall energy is being released. On the right, energy is being absorbed. So exothermic processes are favored by nature. So no surprise when you see an exothermic process. Endothermic processes are unfavored, but mixing is favored because of the whole entropy thing. So it's kind of a balance when we're looking at an overall endothermic process. The fact that it's mixing together is outweighing the fact that it's endothermic. The strengths of these interactions. So you got to look at the different types of interactions. We have the solute and solute interacting. We have the solvent interacting with other solvent, and then we have the solute-solvent interactions. The strengths of all these interactions depend on what type of intermolecular attractive forces are present, or IMAFs, right? Intermolecular attractive forces. So, for example, remember we got hydrogen bonding, dipole-dipole, dispersion forces, or ion-dipole interactions. If I'm taking a look at water, water is polar, and it's got hydrogen bonded. It's hydrogen bonded to either nitrogen, oxygen, or fluorine. So the strength of interaction between water molecules is pretty strong. In this butane molecule, hey, it's nonpolar overall. We're only going to have dispersion forces. Compared to the hydrogen bonding, they're relatively weak interactions. Which brings us to like a general rule, like dissolves like, which basically just means substances that have similar attractive forces will mix more readily than ones with different attractive forces. So my go-to example is oil and water. Y'all are probably pretty familiar that oil and water don't mix. It's the example people use when they're like, hey, these two things don't get along. It's like mixing oil and water. It just won't mix together. And I have a pet peeve, right? People often say, oh, it's because they have different densities. No, that's not why they don't mix. You know, salt and water have different densities, but they mix. So what is it? It's because they have different attractive forces. So if I'm taking a look at oil, oil is a nonpolar particle, which means it only has dispersion forces. Water is a polar molecule that has hydrogen bonding. So because they have different attractive forces, you wouldn't expect these particles to mix strongly with each other, right? So that's why it's, you know, if you're like, all right, well, so what, they don't mix, which one's going to be on top? All right, fine. Oil will be the one on top because it's less dense. But the reason they don't mix, even when you try, is because they have different attractive forces. All right, had to get that off my chest. Summarize. Can you describe what occurs during the process of dissolving at a molecular level? And can you explain the underlying properties that determine if two things will be soluble and the enthalpy changes with such a process? I hope you found that helpful. See you in class. Goodbye.